right now, like every high-definition video you stream or every secure transaction you authorize, it's all being smashed into electrical voltage, right? Or pulses of light.
Yeah, exactly. Just
Yeah.
hurtling along at a fraction of the speed of light.
And it's doing that through these terrifyingly messy racks of blinking metal boxes. I mean, we tend to think of the internet as this ethereal cloud, but it's deeply, unapologetically physical.
Oh, totally.
So today for our deep dive, we are pulling apart the architecture defined in the CompTIA IAA plus 220 1201 blueprints. We're looking at the raw, exposed nerves of a computer network.
Which is an incredibly revealing exercise, honestly.
Right. Our mission here isn't to just review basic networking definitions. We're tearing apart the hardware to see the engineering marvels that actually make the modern connected world function, without collapsing under its own massive weight.
Right, because when you walk into a server room, the towering metal skeleton crammed with cables and jet engine fans, it looks like unfiltered chaos.
Oh, it really does.
But the chaos is an illusion. Once we analyze the physical reality of how these devices negotiate traffic and segment data, you realize it is an aggressively optimized system. It's ruthlessly efficient.
So let's start at the foundational layer. Moving a single frame of data from point A to point B on a local network. If you are hardwired into an enterprise network, you are hitting a switch.
Always, yeah.
We all know local traffic relies on MA addresses for delivery, but the sheer math of that at an enterprise scale is staggering. I mean, a core switch might be processing millions of frames every single second.
Easily.
So how is a physical box keeping track of thousands of unique MA addresses without, introducing massive latency?
Well, the secret is entirely in the hardware.
Yeah.
If a switch relied on a general-purpose CPU and software to evaluate every single incoming frame, the network would just grind to a halt.
It'd be just too slow.
Way too slow. Instead, enterprise switches use application-specific integrated circuits, or ASICs. These are microchips that are hardwired at the silicon level to do literally nothing but evaluate MI addresses and forward frames.
Wow, okay. So they don't even run an operating system in the traditional sense.
No, not really. They process the logic purely in hardware.
And they pair those ASICs with CAM tables, right? Content addressable memory, which I find fascinating because a normal computer memory search asks, what data is stored at this specific address?
Right, but a CAM table flips that completely backward.
Yeah. It asks, where is this specific MSC address located? And the hardware returns the exact physical port number in a single clock cycle, literally in nanoseconds.
It is hardware-accelerated lookup at its finest. The ASIC reads the destination AMC address on the incoming frame, queries the CAM table, and instantly blasts that frame out the corresponding port at wire speed.
So it's isolating that traffic so only the intended recipient sees it.
Exactly, which is crucial for bandwidth conservation.
Mm.
But, that blinding speed only applies to the local subnet.
Right.
When that frame needs to traverse the country, or even just jump to a different department's network, the switch has to hand the problem over to a router.
Because routing is an entirely different engineering challenge. The router operates at layer 3, right, dealing with illogical IP addresses. It's not just looking for a physical machine anymore.
No, it's evaluating the absolute fastest path across the whole web of interconnected networks. It has to process routing protocols, calculate metrics, decrement the time-to-live counter.
Oh, wow, right.
And sometimes even fragment the packet if the next hop has a smaller transmission window, so it requires actual compute power.
And routers bridge entirely different physical topologies, too. A router can ingest a packet coming in from a fiber optic connection, translate it, and push it out over a copper serial line.
Yep, it is fundamentally a boundary device.
Yeah.
But the engineering reality of modern networks is that we rarely keep these functions in isolated boxes anymore. The line is really blurred with the adoption of layer 3 switches.
Or multi-layer switches. The hybrid approach. So you're taking the hardware-accelerated ASIC switching for local MP traffic and, baking the IP routing logic into the exact same silicon?
Exactly. So if a packet is destined for the local network, it's switched at nanosecond speeds. But if it's destined for another subnet, the hardware routes it right then and there.
Without ever having to send it to a separate physical router box.
Right. It dramatically reduces those hairpin turns data used to have to take inside a server room.
Yeah.
You achieve wire speed routing because the routing table itself is cached into the hardware forwarding logic.
Okay, so the logic of the traffic cops makes sense. But let's look at the physical vulnerability of this system. Because in a corporate environment, you have hundreds of employees plugging into these
Yeah,
switches.
a lot of moving parts.
And the standard practice is running permanent cable from the wall jack at the desk up through the ceiling and punching it down into the back of a patch panel in the server closet.
Hmm.
Then you use a short patch cable to connect the front of the panel to the switch. Now, I used to wonder why we couldn't just run one continuous cable from the desk straight into the switch. But it actually comes down to the metallurgy of the wires, doesn't it?
Yeah, the physical composition of the copper makes all the difference here. The permanent cable running through the walls uses solid core copper wire. It's excellent for transmitting data over long distances with minimal degradation.
Ah,
But it is incredibly brittle. If you bend solid core wire back and forth, you create microfractures in the copper. And those fractures change the electrical resistance of the wire.
which I'm guessing destroys the high-frequency data signal.
Oh, absolutely. It
Yeah.
causes massive drop packets.
Okay, so if you ran solid core wire straight into a switch,
Yeah.
the constant plugging and unplugging or just shifting cables in the rack would literally fracture the internal copper.
Right. That's exactly why the patch panel exists. It locks that fragile solid core wire into a punch-down block where it will never, ever move.
That makes so much sense. And then for the final connection between the patch panel and the switch?
For that, you use a patch cable made of stranded copper. It's made of dozens of microscopic copper threads woven together so it's highly flexible. It can withstand constant bending.
And if the plastic retention clip breaks, you just what, throw away a $2 3-foot cable?
Exactly. Way better than paying a technician to rip open the drywall to replace a fractured 100-foot cable.
So it's all about mitigating physical failure points. Okay, let's unpack this a bit more. Because once we have everyone safely patched in, we run into a scaling problem.
Big time.
If you take an unmanaged switch, like the kind you buy off the shelf for a home lab, it treats every plugged-in device as a part of one massive broadcast domain.
Right. Everything hears everything.
Right, so if we scale from a 10-person office to a 10,000-person enterprise campus, the background broadcast traffic alone would be insane. Devices shouting out to find printers or resolving IP addresses, it would saturate the links and bring the network to its knees.
The sheer volume of ARP requests would cause a literal broadcast storm. This is exactly why enterprise environments require managed switches.
Okay, so how do they solve it?
They allow network engineers to logically segment the network using VLANs, virtual local area networks. You could have 50 people plugged into the exact same physical switch, but through the management interface, you configure ports 1 through 24 for accounting and ports 25 through 48 for engineering.
And internally, the switch is using 802.1q tagging, right?
Yes, exactly.
It physically inserts a tiny tag into the header of every data frame identifying which VLAN it belongs to. So even though accounting and engineering are sharing the exact same silicon, the switch treats them as entirely isolated networks.
Right. The accounting broadcast traffic never touches the engineering ports. You solve the physical scaling problem with logical segmentation.
That is brilliant.
And beyond segmentation, managed switches give you quality of service, or QoS, because when network congestion happens, and it always happens, the switch has to decide which packets get dropped and which get through.
So with QoS, you manipulate the priority queues. Like you instruct the switch to always process voice over IP packets before standard file transfers.
Exactly. Because a delayed file transfer just means a download takes 2 seconds longer. But a delayed voice packet, that means the CEO's phone call sounds like a garbled mess.
Yeah, that's a resume-generating event right there. Managed switches also give us visibility through port mirroring, don't they?
They do, yeah, which is vital for security. If you suspect a machine has been compromised, you can't just unplug it because you'll lose the live forensic data.
Right, you need to see what the malware is doing.
Exactly. Instead, you configure the switch to take a perfect duplicate of every single frame entering and exiting that specific port and mirror it over to an intrusion detection system. It's completely invisible to the attacker.
It acts like a silent wiretap at the hardware layer. But all of this rigorous management gets super complicated the moment we introduce wireless networks.
Oh yeah, wireless changes everything.
This is where we need to talk about access points, and we really need to draw a hard line between enterprise gear and consumer gear here. Because, wait a second, the box sitting in my living room gives me Wi-Fi, but you're saying an access point isn't a router.
Not in the enterprise, no. That ISP box in your house is acting as a router, a firewall, a switch, and an access point, all crammed into one plastic shell.
Okay.
But in an enterprise environment, An AP is a very specific, isolated piece of hardware. It's essentially just a dumb Layer 2 bridge.
Wait, really? It doesn't do any routing?
Zero. The enterprise access point performs absolutely zero IP routing, no network address translation, and no firewalling. Its only job is to bridge 802.3 Ethernet frames from the wired network into 802.11 wireless frames for the airwaves, and vice versa.
So it's just doing MSC address translation.
Exactly. And by stripping away all that routing logic, the AP can dedicate all of its processing power and radio antennas to handling high-density wireless traffic.
Which means you can scale coverage infinitely. Like if you need Wi-Fi in an auditorium, you don't add more routers, you just hang 10 access points from the ceiling, all feeding back into your managed switches.
Right. But the moment you have wireless data flying through the air and thousands of internal users, you have to fortify the perimeter. You need a firewall.
For sure. Now, traditional firewalls operate on a relatively simple premise, right? Stateless or stateful packet inspection based on ports and IP addresses.
Yep, very basic. If traffic tries to enter the network on TCP port 80, the firewall checks its access control list. Port 80 is designated for HTTP web traffic. If the rule says web traffic is allowed, the firewall lets it through.
And if it hits port 3389, which is remote desktop, it drops it.
Exactly.
But relying on port numbers feels fundamentally flawed in modern security because malicious actors know exactly what those rules are. They just bypass port blocking by tunneling malicious traffic right through the ports you're forced to leave open.
Yep, they just hide in plain sight.
Right. If a hacker configures a reverse shell to communicate over port 80, a traditional firewall looks at the port number, assumes it's just someone browsing a website, and waves the attacker right through the front door.
Because the traditional firewall is basically only reading the shipping label on the outside of the box. It has no idea what is actually inside.
What's fascinating here is how this vulnerability forced the evolution into next-generation firewalls, utilizing deep packet inspection.
Right. To use a medical analogy, if a traditional firewall is like a security guard checking IDs at the hospital entrance, a next-generation firewall is an MRI machine.
Oh, I love that. It's actively scanning the biological makeup of the data.
Precisely. Deep packet inspection strips away the headers and looks at the actual payload of the packet in real time. It analyzes the application layer signatures.
So the firewall sees the traffic coming in on port 80, unpacks it, and actually recognizes the behavioral signature of remote desktop software or a known malware strain.
Yes. It completely ignores the port number, identifies the true nature of the application, and severs the connection instantly.
And because these next-gen firewalls possess so much compute power to do that at gigabit speeds, enterprise networks often use them as multi-purpose security appliances. They act as VPN concentrators, managing encryption for remote workers. Many even operate as forward proxies.
And the proxy function is incredibly powerful. Instead of allowing an employee's computer to connect directly to a potentially dangerous external web server, the firewall intercepts the request.
So it's a middleman.
Exactly. The firewall itself establishes the connection to the external server, downloads the web page, executes the code in a sandbox to ensure it isn't harboring ransomware,
Wow.
and only then does it pass the sanitized data back to the employee's internal machine.
So the internal network never actually touches the public internet. It's a brilliant air gap strategy. But, there is a completely different engineering marvel happening on these networks that doesn't involve data at all.
Oh, right. Power.
Yes, electricity. Let's look at power over Ethernet, or PoE. Sending DC power over the exact same copper wires that are carrying high-frequency data without causing interference or frying the devices.
The implementation of PoE fundamentally altered building architecture. It removed the dependency on high-voltage electricians.
Which is huge for IT budgets.
Huge. If you want to install a security camera on the exterior of a building or an access point in a drop ceiling, you no longer need to run electrical conduit and install an AC wall outlet next to the device.
Yeah.
You just run a single Category 6 Ethernet cable.
And it provides both the gigabit data connection and the electrical power. But the engineering challenge there is massive. If you have a switch pushing out power, how does it know it's not going to accidentally push voltage into a legacy device, like a non-PoE laptop, and instantly fry its motherboard?
That's the genius of it. The standard relies on a very elegant low-voltage handshake. Before a PoE switch applies any meaningful power to the line, it sends a tiny, harmless pulse of electricity down the cable to measure the resistance.
Okay. What's it looking for?
It's looking for a very specific 25,000 ohm signature on the receiving end. If the end device presents that exact signature, the switch knows, okay, you are a PoE-compatible device,
Yeah.
and then it negotiates the required wattage and turns on the power.
And if it doesn't see that signature,
It just treats it like a standard data-only connection. No power is sent.
here's where it gets really interesting. The evolution of that wattage is staggering. The original 802.3 AFPoE standard pushed about 15.4 watts, which was plenty for a basic desk phone. Then we got PoE plus S pushing 25.5 watts to run things like pan-tilt zoom security cameras with actual mechanical motors.
Mm.
But the newest standard, PoE plus plus F, also known as 802.3 BT, can push up to 71.3 watts of usable power to the end device.
71 watts delivered entirely over data cables. That is enough power to run multiple thin client computers, point-of-sale registers, and even full-size laptops, completely eliminating their need for a power brick.
That's wild. And it's typically delivered in one of two ways, right? If the managed switch itself generates the power, it's called an end span.
Right, but if you have an older non-PoE switch that you don't have the budget to replace, you can install a mid-span.
A power injector. So you patch the data cable from the old switch into the midspan, plug the midspan into the wall to draw AC power, and it injects the DC voltage onto the unused pairs of the Ethernet cable before sending it out to the access point.
It's an excellent stopgap. The key engineering constraint to remember there, though, is backward compatibility. A brand new PoE++ switch can easily negotiate down to power a 15-watt legacy desk phone.
But it doesn't work in reverse.
Exactly.
Huh?
An older PoE switch physically cannot push enough amperage to boot up a modern 70-watt device.
Makes sense. So our internal network is fully powered, logically segmented, deeply inspected, and routing efficiently. But all of this infrastructure is useless if we can't reach the outside world. The data has to hit the WAN, the wide area network,
Yeah, we need the internet.
and the hardware required to bridge that gap depend entirely on the physical medium buried in the street outside the building.
Right. If your enterprise leverages the existing coaxial infrastructure laid down by television providers,
Right.
you'll utilize a cable modem operating on the DOCSIS standard.
Data over cable service interface specification.
Yep. DOCSIS is highly resilient. It bonds multiple downstream and upstream channels together over that shielded coax cable to easily deliver multi-gigabit speeds.
But if you are in a location where cable isn't an option, you might be relying on DSL, digital subscriber line, which is fascinating because it overlays high-frequency digital signals directly on top of legacy analog copper telephone wires.
It is, but DSL has a brutal limitation dictated by the laws of physics. It operates on unshielded twisted pair copper, which means it suffers from severe signal attenuation.
The electrical signal literally bleeds into the surrounding environment as heat the further it travels.
Exactly. With DSL, your physical distance from the provider's central office dictates your bandwidth. If your building is beyond a radius of roughly 10,000 feet,
Which is less than 2 miles, right?
yeah, less than 2 miles, the attenuation is so severe at that point that the high-frequency data signal degrades into unreadable noise.
Which is why the ultimate goal for any enterprise is fiber optic cable, swapping electrical voltage for pulses of light. And if you have fiber terminating in your server room, you aren't using a modem. You are using an ONT, an optical network terminal.
Right, because modems exist to modulate and demodulate analog and digital signals. An ONT operates differently. Fiber optics rely on total internal reflection, bouncing photons of light down a glass core.
So the ONT's job is to take those incoming pulses of light and translate them back into electrical signals for your copper-based routers and switches.
Exactly.
And modern ONTs utilize wave division multiplexing, right? They aren't just reading one stream of light. They are reading multiple different colors or wavelengths of light simultaneously over the exact same glass strand, which is how fiber achieves such absurd, symmetrical gigabit bandwidth.
The multiplexing allows for bidirectional traffic without interference. And structurally, the location of this ONT or the cable modem, depending on your connection, is critical. In enterprise architecture, this device serves as the demarc.
The demarcation point.
Yes.
If we connect this to the bigger picture, it's the legal and physical boundary line. If a backhoe cuts the fiber in the street, the issue is on the ISP's side of the demarc, and they have to dispatch a crew.
Right. But if a managed switch dies in your rack, it's on the local side of the demarc, and your internal IT team has to fix it.
It clearly defines the scope of responsibility. And to bring this entire architectural journey full circle, we have to look at how a single device crosses that boundary to actually participate in this network. Because every single piece of hardware, from the massive servers to the PoE security cameras to the laptop on your desk, It requires an NIC, a network interface card.
The physical entry point.
Whether it's an integrated chip on a motherboard or a dedicated expansion card managing multiple 10 gigabit fiber connections, the NIC handles the physical layer signaling. And most importantly, every NIC comes permanently burned from the factory with its own globally unique MAC address.
Which brings us right back to our CAM tables.
Exactly. The ASIC on the switch learns that NIC address the moment the NIC powers up, and the incredibly complex nanosecond speed routing of the internet begins all over again.
It's beautiful, honestly.
So what does this all mean for you? When you understand the mechanics of this, the solid core copper, the ASIC hardware logic, the deep packet inspection, and the low voltage PoE handshakes, you realize there is no magic to the cloud. You are equipped to walk into any data center, look at that intimidating blinking rack of hardware, and actually read the hidden anatomy of how information flows.
It gives you a profound appreciation for the physical infrastructure that sustains our digital lives. And, as we map this evolution, particularly the leap in power over Ethernet, it raises a really compelling architectural question.
What's that?
Well, if PoE++ is already securely negotiating and pushing over 70 watts of DC power through data cables to run laptops and monitors, we are witnessing the real-time convergence of data and power. Are we fast approaching a threshold where traditional high-voltage AC wall outlets become obsolete for daily electronics, completely merging our digital networks and our electrical grids into a single, unified infrastructure?
Wow. That is something to think about next time you plug in your phone.